Today we have Mark Krumholz here speaking to us. Mark got his bachelor's degree from Princeton University. Then he came out here to Berkeley for his PhD, after which he got a prestigious Hubble Fellowship that he took back to Princeton for 3 years before getting a faculty position at UC Santa Cruz, where he's at right now. And today Mark will discuss for us the star formation rate. Mark.
Well, thank you. So thank you for inviting me, and before I begin, let me just say, if at any point anything I say is unclear, or I say something that doesn't make any sense, please feel free to interrupt me. I'm happy to have questions during the talk as well as after. So I'm going to try and tell you a little bit today about the star formation rate, and I sort of feel happy to be doing this at the SETI Institute because star formers have sort of the honor of we have the one term in the Drake equation that's probably known to within a factor of 2. So, we're sort of unique in that. So what I'm going to do is try and divide this talk into sort of 2 halves. All right. The first one is going to be a sort of introduction to how do we go about measuring the star formation rate? What's the technique we use to say that we know what the star formation rate is? All right. So that's going to be sort of the first half. And for the second half, I'm going to talk a little bit more about my research, which is why is the star formation rate what it is? What are the physical mechanisms that control when and where stars form? So that's what I'm going to do for the second half of the talk. But let's begin with measuring the star formation rate. How do we actually go about measuring the rate at which stars are forming in our galaxy or in an external galaxy? All right, well, in order to explain that, I have to start by telling you a little bit about massive stars. All right, now, the first thing you should know about massive stars is that they are extremely bright. So this is just a sort of very simple toy model calculation. If you're actually doing real work in this, you do much more sophisticated calculations. But this is just a sort of toy model that illustrates the point. Massive stars are very bright. So here on the x-axis we have mass in solar masses, and here on the y-axis we have luminosity. And what you can see is as we go from, say, 1 solar mass, our sun, which is about 1 solar luminosity, to 100 solar masses, that's more than 10 to the 5 L sun. All right, so there's a huge increase in luminosity corresponding to a change of a factor of 100 in mass. So massive stars are extremely bright. They're not only extremely bright, they're very, very hot. So here, same x-axis, and now what I'm showing you is the effective temperature of the star. All right, and this is just the temperature of a black body radiator of the star's size that's putting out as much light as the star is putting out. All right, now stars are not really black bodies. They have all sorts of complicated spectral features. But to get a sense of how hot the radiation the star is putting out, this is a reasonably good way of getting a handle on that. And what I want you to notice is that, again, we go from the sun, which has a surface temperature of around 6,000 Kelvin, up to, for a 100 solar mass star, a surface temperature that's approaching 10 to the 5 Kelvin. Now, one thing I've added to this plot, which is significance, is KT equals 1 Rydberg. All right, so that is the temperature at which Boltzmann's constant times that temperature is equal to 13.6 eV, which is the ionization potential of hydrogen. All right, now that's significant because the interstellar medium is mostly hydrogen. So photons with energies below this line are not capable of ionizing hydrogen atoms, whereas photons with energies above this line are. All right, so massive stars are very, very bright. We saw they've got a big luminosity. And because they're hot, they're putting out a lot of their energy in the form of photons capable of ionizing hydrogen. And in fact, that's what I've plotted here. So this is the rate of output of ionizing photons. All right, so this is ionizing photons per second as a function of the mass of the star. All right, and you see that this is even steeper than the 2 graphs I showed you before. All right, we go from the sun, which is putting out, by the standards of a massive star, basically no ionizing photons, up to stars that are putting out 10 to the 49 or 10 to the 50 ionizing photons per second. All right, now that's going to become important in a moment, but for now, just hold that thought in your mind, that massive stars put out a huge number of ionizing photons compared to low-mass stars. And there's one last thing about massive stars I have to tell you, which is they're very, very short-lived. All right, so what I've plotted here is an estimate of the main sequence lifetime of a star as a function of its mass. All right, and you'll see it goes from, for the sun, with a lifetime that's more than a gigayear, all right, something like 10 gigayears, down to, say, a 100 solar mass star, where we're talking about a lifetime of more like a few million years. Very, very short by interstellar standards. All right, so massive stars are very bright, they're very hot, they put out a lot of ionizing photons, and they're very short-lived. And this combination of characteristics is the trick that we exploit to measure the star formation rate. So the short lifetime of massive stars means that the number of massive stars that are present in any given region is more or less proportional to the instantaneous star formation rate in that region. All right, and that's because the rate at which star formation rates change is very slow compared to a few million years. It is generally not the case, if we look at a big piece of a galaxy, that the star formation rate in that galaxy is going to be fluctuating over a few million years. All right, so the time it takes to go around the Milky Way once, where we are, is about 200 million years. All right, so we wouldn't expect any significant changes in the rate at which the Milky Way is making stars to occur on timescales that are much smaller than that. All right, now, the time that a massive star lives is only something like 3 million years, and what that means is that the number of massive stars that are present at any given time is more or less just proportional to the rate at which they're forming. So if you can measure the number of massive stars, then you can measure the star formation rate. All right, now, how do we measure the number of massive stars? Well, that's actually made easier by their characteristics. In particular, their high luminosities make them visible from large distances. They're easy to find. All right, and the fact that they're very hot, they put out a lot of ionizing photons, means that they do things that make them stand out. They're easier to pick out, and I'll talk about that in a second. So if we want to measure the star formation rate, we therefore have a two-step problem. We need to measure how many massive stars there are in a given volume that we're interested in measuring the star formation rate in, and we need to convert that into a star formation rate. All right, so how do we do those two steps? All right, well, the first step, measuring the mass of stars, the general idea is to exploit this phenomenon called H2 regions. All right, now, these are very, very pretty, and I've just taken some random pictures of H2 regions. All right, this is in our galaxy, these two are in other galaxies. All right, and you see there are these bubbles of bright shining gas. All right, so what's an H2 region? All right, well, for those of you who are primarily planetary scientists, not astronomers, at this point I need to let you into horrible, horrible astronomy notation. All right, this is terrible, and on behalf of my field, I apologize for it. So, astronomy notation, we refer to the neutral state of an element as that element Roman numeral 1. We refer to the state of the element when it's been ionized once as that element Roman numeral 2. If it's been ionized twice, that element Roman numeral 3. Now, hydrogen only has one electron, so we have H1, neutral hydrogen, and we have H Roman numeral 2, ionized hydrogen. What makes this particularly obnoxious is that we also have H subscript 2, molecular hydrogen. Fortunately, that won't make an appearance until later in the talk. For now, we're going to focus on H Roman numeral 2. So here's the trick. Most of the interstellar medium is neutral hydrogen. However, I just told you that massive stars put out a lot of ionizing photons, and those ionizing photons blow a bubble around the massive stars of ionized hydrogen. All right, so hydrogen atoms that are too close to the massive star get hit by an ionizing photon, knocks the electron off, you get a bubble of H2. And these things light up very well, which makes them easy to pick out. All right, and I'll talk about next why they light up and how we can use our understanding of the physics of how they light up to measure the rate at which ionizing photons are being injected into them. All right, so just to show you a sense of how we can pick these things out, here I've got spectra of 4 different galaxies, ranging from a galaxy that's basically not forming stars at all to progressively more and more star formation dominated galaxies. And you will notice a dramatic change in the character of these spectra. All right, this spectrum doesn't vary that much. It's got some absorption lines. It's fairly smooth. This spectrum, on the other hand, has all these spiky features. All right, and these spiky features stand out a factor of 10 above the sort of background level. All right? You may not be able to read it from the back, but the scale here is from 0 to 1.2, and the scale here is from 0 to 14. All right, now, those spectral lines have been identified, and two of the most prominent ones you see are the H-alpha line, that's 65, 63 angstroms, and the H-beta line at 48, 61. All right, now for those of you who are not spectroscopists, those are recombination lines of hydrogen. So the fact that we get all this non-thermal emission, all these lines, makes it easy to pick out the H2 regions. So where do those lines come from? Well, let's look at an H2 region. So we've got a region where most of the hydrogen is ionized. So we've got free protons and free electrons running around. And every so often, one of those free protons will encounter one of those free electrons. They will interact, and they will emit a photon and become bound. They will recombine. All right, so we go from free proton plus free electron to bound atom, and a photon is emitted. Now, that's a continuum photon. It's not so easy to pick out. All right, but the second step is easy to pick out, because some of those recombinations will result in atoms that go directly into the ground state of neutral hydrogen, but some of the recombinations will leave the atom in an excited state. All right, and so what happens is, let's say that there's a recombination that drops this electron into the 4p level of the hydrogen atom, of the neutral hydrogen atom. Well, this is an excited state, and so that atom can then radiatively decay. So it drops down, emits a photon, drops down, and it keeps doing that until it gets back to the ground state. And each one of these photons that's emitted as it drops down in levels is a line photon. And so a lot of the energy comes out in this line emission process. And those lines, being spectral lines, are very, very easy to pick out. And in fact, if I show you these pictures, all right, the sort of reddish color that's evident in a lot of these pictures is, it's that line, is the H-alpha. All right, now, what's nice about this is that this is a problem we know completely how to solve. All right? Hydrogen has the virtue of being the one element that we can solve the hell out of. All right? Yes, question?
I was just wondering, which is the hydrogen alpha transition?
So the H-alpha is a recombination from the 3 to the 2. All right? H-beta is from the 4 to the 2. All right? So yes, the recombinations that go to or decays to the second state are the H series, which is the Balmer series. All right? Decays to the third state are the Paschen series. Decays to the ground state are the Lyman series. The reason that people tend to talk about the Balmer series is that those show up in the visible. All right, whereas the Paschen series is mostly in the infrared, and the Lyman series is in the ultraviolet. All right, so what's nice about this is that this problem we can solve. All right, that is, if I've got a region of ionized hydrogen, a plasma, I can compute quite precisely what are the relative rates of recombination to the various excited states. What's the rate of recombination directly to the ground, to this state, to this state, to this state? All right, that's a problem that we can solve from first principles easily. Well, not easily, but we can do it. And moreover, once something is in one of these states, the rate at which it decays, the probability that it goes to there versus to there versus to there directly, all of those rates are also calculable from first principles. It basically involves writing down a bunch of spherical harmonics and integrating them. All right, and you could actually do most of it on pencil and paper, or even better, you can get a computer to do it for you. All right, so all of these rates are known. And what that means is that this is a completely solvable problem. I know, per recombination, how many photons I should get out in each and every one of these lines. So that is, if I measure the rate at which photons are coming out in one of these lines, I can turn the problem around and figure out what's the rate of recombinations that's required to power that emission. So what this means is that I can take something I can directly observe, this line emission, and turn it into a rate of recombinations. All right, so how do I measure massive stars? Well, the first thing I do is I measure what's the ionization rate. Because in one of these regions, the recombination rate and the ionization rate are about equal. All right, if I turned off the star, if the star stopped emitting ionizing photons, then very quickly the hydrogen would recombine and go back to being neutral. So the rate at which I'm injecting ionizing photons is balanced by the rate at which things are recombining. If there's an excess, if there are more ionizing photons being injected than there are atoms recombining, then I will very quickly ionize a bunch more atoms until the recombination rate is in balance again, and vice versa. If there aren't enough ionizing photons being injected to keep the gas ionized, a bunch of it will recombine until the recombination rate drops low enough that I'm in balance again. So the ionization and recombination rates are in balance. I can measure the recombination rate, and I can therefore convert that to an ionization rate. All right, and so here are some examples of this conversion. All right, and so what I've got here is a formula that says for a given ionization rate, this is how much luminosity I should get in these two particular lines. All right, and there are other lines you can use which are in different parts of the spectrum, in particular in the radio. All right, so that's one technique. Now that's actually our most useful technique extragalactically, because a lot of these lines are in the optical. Within the galaxy, it's a little trickier, and the reason it's a little trickier is because optical light has a hard time traveling through the plane of the galaxy. There's a lot of dust in the way. All right, so instead of doing optical lines, we use a somewhat different technique, all right, called free-free emission. All right, so what's free-free emission? Well, this previous mechanism I talked about was free to bound. All right, I had free atoms, they become bound. Free-free is that if an electron encounters a proton, they don't have to become bound. They can simply scatter inelastically off each other and still remain unbound to one another, but in the process emit a photon. All right, and the mechanism here is pretty simple. I've got a proton, I shoot an electron by it, the electron accelerates in the proton's electric field, all right, and anytime a charge accelerates, it emits light. And at the temperatures found in H2 regions, it mostly comes out in the radio. So I get all these radio photons. Now the nice thing is, again, this is a solvable problem. The rate at which I get these free photon emissions is proportional to the rate at which protons and electrons encounter one another, which is proportional to the recombination rate. So I know that for every recombination, I should get a certain amount of energy coming out in free emission. So same trick. I measure the free emission rate, and I can turn that into a recombination rate, which I can turn into an ionization rate. All right, and here's the sort of latest conversion between ionizing photon emission and luminosity in free at this particular radio wavelength. Now, those of you who are aficionados will recognize this. This is one of the wavelengths that's used by the Planck satellite. All right, so we know how to measure the ionizing photon emission rate. How do we convert that into a star formation rate? Well, to do that, we need to use a technique called population synthesis. All right, and here's the basic idea. Suppose we've got some region where stars are forming at a certain rate. All right, and I'll measure my rate in mass per unit time. That's this m dot star. All right, and moreover, the initial distribution of those stars as they're formed is this function xi, which is the number of stars per unit mass. This is the mass distribution. The way you can think of this as is, well, all right, not all the stars that form have the same mass. There are going to be a lot of little stars. There are going to be a few big stars. So let me imagine that I have mass bins, 1 to 2 solar masses, 2 to 3, 3 to 4, 4 to 5. Let me just count how many stars are in each of those bins. That's what this function is. All right, so I can compute the total ionization rate simply by integrating over this distribution. So I count how many stars are in this bin, how many ionizing photons per second, and I've switched notation here, I'm sorry, from S to Q, how many ionizing photons per second are emitted by a star of that mass, and how long will that star emit those photons? What's its lifetime? And then I just add up all the bins. That's what this integral represents, and I multiply by the overall star formation rate. And that gives me the expected ionization rate from a population of stars that is forming at a certain rate. Now, I've already said I can measure this, so the last step is I just have to be able to evaluate this integral. Now, two of these things, Q, that is the rate of ionizing photon emission, as a function of stellar mass, and the lifetime as a function of stellar mass. I already showed you those. And those are well known from stellar evolution theory. All right, that's a problem that's been solved for 50 years. So the last thing I need is this IMF. All right, so as I said, we know the lifetime and the ionizing luminosity from stellar evolution theory. The IMF is a little trickier. We know it empirically. We don't really understand it theoretically, and I could in fact give you an entire talk and then some on the origin of the IMF and the problems associated with it. Fortunately, it seems to be roughly universal. So what's plotted here is measurements of this initial mass function from a bunch of different regions, all right, and this is taken from a paper by Pavel Krupa. All right, so the different colors, the different symbols here represent different regions where the mass distribution of stars has been measured. All right, so just to walk you through this plot, this is the logarithm of the mass. So that's 0.1 solar masses, 1 solar mass, 10 solar masses, etc. All right, and this is the mass per unit bin rather than the number per unit bin, but obviously you can convert one into the other. All right, so what you see is the peak is somewhere between 1 and 0.1 solar masses. Those are the most common stars, and that's where most of the mass is. More massive stars are progressively rarer. All right, but if I know this function, then I can go and evaluate this integral. And what I get is a conversion between the star formation rate and the rate of ionizing photon emission. All right, so we've already talked about how I can measure this, and now I can measure this. All right, so that's how we go about measuring the star formation rate. So I will not walk you through exactly who has done this. I'll just mention the sort of two most recent and reliable measurements. All right, so one by Williams and McKee, using a catalog of H2 regions measured in the radio and then based on their free luminosity. And they get about 3 solar masses per year. All right, and the other is, excuse me, not Planck, WMAP. All right, this is the Wilkinson Microwave Anisotropy Probe. So this is a satellite that has gone up to measure the cosmic microwave background radiation, but in the process, it's done a radio survey of the entire sky, and one of the things it's gotten out of that is a map of free emission from the entire sky. All right, and they get 1.3 solar masses per year. All right, and the sort of statistical uncertainties, just the measurement uncertainties here, are less than a factor of 2. Now, as is often the case in astronomy, the major uncertainties are not the measurement errors, they're the systematic errors. So what are the systematic errors here, and how much should you believe these results? Well, all right, so the major systematic uncertainties are the IMF, the form of the ionizing luminosity, and dust absorption. So let me just mention each of these in turn. The IMF, as I mentioned, is a huge topic, and it seems to be universal. And we're assuming that it's universal and that we've measured it properly when we compute this conversion factor. Now, we don't have any evidence that the IMF does vary, but we also don't really understand it. And so it is entirely possible that it does vary at, say, the factor of 2 level, and we wouldn't really know it. And it's very hard to detect this measurement detect this variation because we have a real problem of we can't measure the dog, we can only measure the tail of the dog. All right, so massive stars are the only ones we can measure based on this H2 region technique. All right, all the luminosity, all the ionizing photons are coming from the massive stars. But by mass, they're a completely negligible fraction of the population. All the mass is in the low mass stars. So effectively what we're doing is measuring the massive stars and then extrapolating to the low mass stars. And that means that if we screwed up a little bit in the ratio of massive stars to low mass stars, that could easily mess up our measurement. And so that's probably the biggest systematic uncertainty, which is why I've helpfully colored it yellow. What are the other uncertainties that go into this? Well, a smaller one is the ionizing luminosity as a function of mass at large masses. All right, and this is just because ionizing luminosities are not something that's easy to measure directly. All right, and they're not easy to measure directly just because, well, you can never see the ionizing photons directly because they don't get to you. They get absorbed by the interstellar medium before reaching you. And so you have to trust our stellar evolution models. And you can try and check them, but the checks become increasingly scarce and hard to come by as you go to higher and higher masses. The most massive star whose mass we really definitely know absolutely from Newton's laws is about 83 solar masses. Whereas this distribution, if I go back, went up to 100 and something. All right, so out here at 100 solar masses, we have no real way to check those. Now, we do pretty well at 83 solar masses, and so the extrapolation isn't ludicrous, but you could legitimately worry about it. All right, and a final bugaboo there is dust absorption, all right, which is that I've got these stars and they're putting out ionizing photons, and I said, well, I'm going to assume the rate at which those ionizing photons are produced is equal to the rate at which recombinations happen. But that's only true if every ionizing photon actually ionizes a hydrogen atom. It could also be absorbed by a dust grain. And if it's absorbed by a dust grain, well, it'll heat up the dust grain, but it won't give rise to free emission or H-alpha line emission or anything like that. All right, and so that gives you an uncertainty as what fraction of your ionizing photons are being absorbed by dust. Now, there are good both theoretical and empirical reasons to think it can't be a large fraction of them. But there is a dust correction in here of about 25%, and that does contribute to the uncertainty. So how much should you trust these numbers? And incidentally, the difference between these two numbers is almost entirely due to differences in the IMF they assumed. All right, if you actually correct these two to the same IMF, they're the same to within a few tens of percent. Yes? So initial mass function. Sorry, I should have. If I didn't say that, I should have. The initial mass function, the distribution of stellar masses at birth.
Can you cut off the stars on large sizes? Is there a cutoff where you don't?
This is an excellent question, which is debated. The empirical evidence seems to suggest that yes, there is an upper mass limit of something like 120 to 150 solar masses. This is debated because as you go to more and more massive stars, they become just intrinsically rarer. And so it's actually a tricky problem to distinguish. There is an absolute physical upper mass limit from it just so happens that my sample wasn't large enough to include a 200 solar mass star because only one in 100 million stars is that massive. All right, so that's why it becomes tricky. But that actually that's not a huge influence on this uncertainty. Really, what could screw this up is, all right, so here, the slope of this line at high masses, all right, so the red hatched region there is supposed to show you the sort of range of uncertainty. And if I assume that the slope looks like this versus that it looks like this, that'll generate a factor of 2 change in this conversion factor. So that's the big uncertainty, is the slope of this at the high mass end. All right, so there's your answer. Stars form in the Milky Way at a rate of sort of 1 to 3 solar masses per year. All right, and I think we can be fairly confident in saying that that's an answer that's good to within a factor of 2. All right, so now let me move on. Oh, yes, before I go on, question.
In your error bars, you showed, I guess, bigger error bars down to the smaller stars. I wondered why.
Oh, here?
Yeah.
Well, okay, so why are the error bars big down here? The error bars are big down here because this is getting into a regime where these things are extremely dim and hard to find. So there are lots and lots of these things, but they're extremely dim, and so they're hard to measure. All right, so the sort of sweet spot between, where there are enough objects that we have good statistics and where they're bright enough that we can actually find them is sort of around here. Yes, question?
At 1.3 to 3, is that the net formation? So 1.3 to 3 over how many stars are dying?
No, so this is only the star formation. This is only the rate at which stars are forming. I have not corrected for the stellar death rate, but the stellar death rate is going to be much less than this because most of the mass here is going into stars that are 1 solar mass or less, and those stars have such a long lifetime that basically the death rate for them is close to 0. So most of the mass here is actually going into stars that have ages, that have lifetimes as long as the age of the universe. All right, other questions before I go on? You'll have to stick your hand up high since I'm being blinded. All right. Okay, so the second half of the talk. So I've told you about measuring the star formation rate. Here is where we get into trouble. All right, because we'd like to understand where this comes from, and this is my business. So I'm illustrating here the proper attitude of a theorist towards observations. All right, and the problem is that if, as a theorist, you actually start to look at the observations seriously, you get yourself in trouble and you wind up looking like, well, a monkey. So, I'm going to try and tell you just a little something about the theory of the star formation rate. And I should say that this is an immense topic, and I'm just going to talk about it a little bit. So what's our embarrassment? Well, we've got a couple, but our first embarrassment is that star formation is too slow. All right, so the disk of the Milky Way galaxy contains about 10 to the 9 solar masses worth of gas in giant molecular clouds. These are the dense interstellar structures that form new stars. And for those of you who are not astronomers, I should be clear that dense here is a relative term. All right, so dense here means something like about 100 atoms per cubic centimeter, which is vacuum by any terrestrial standard, but is a factor of 100 denser than the mean of interstellar space. All right, so dense, 100 atoms per cubic centimeter. All right, now, if these clouds were sort of just collapsing into stars at the rate you'd expect for gas of that density, well, the time it would take a cloud to collapse would be a few million years. All right, and so being a theorist, I am skilled in the art of long division. All right, so I divide, in fact, this isn't even long division, 10 to the 9 by 4 million years, and I get 250 solar masses per year. Whereas, you may remember a couple slides back, the actual star formation rate is closer to 2 solar masses per year. So we've got a factor of 100 discrepancy. All right, and if you repeat this exercise in other galaxies that look like the Milky Way, you come up with this same factor of 100. Now, a factor of 100 is embarrassing even to an astronomer. All right, and it's no better if we go to starburst galaxies. So these are galaxies that have star formation rates much higher than the Milky Way. And here's an example. This is the galaxy ARP 220. All right, so its interstellar medium has about 10 to the 9 solar masses in molecular gas, the same total mass of interstellar molecular gas as the Milky Way. It's just that in ARP 220, all of this gas has been crushed into the central half a kiloparsec of the galaxy. So in the Milky Way, all that molecular gas is spread out over a sort of 10 kiloparsec size disk. In ARP 220, all of that gas has been crushed into the center half a kiloparsec. So the density is much, much higher. The free fall time, the time it would take something to collapse if there were nothing but gravity acting on it, is correspondingly smaller, and I do division again, and I get 5,000 solar masses per year, whereas the actual star formation rate is more like 50 solar masses per year. So still a factor of 100 problem. Now, maybe you could say, all right, well, the problem is I'm looking at this gas at a density of 100 particles per cubic centimeter. All right, and this isn't that dense. Maybe I'm wasting my time, I'm confusing myself. This 100 particle per cubic centimeter gas, most of it's inert, it's not going to form stars. Let's go look at denser gas. All right, now we can do that by looking at different molecules. All right, so this is an observation using the HCN molecule, which, if anyone's really curious, I will explain why, but for now, just take me at my word. This is a molecule that you only see emission from it from gas whose density is at least about 10 to the 5 particles per cubic centimeter. So what I've done here is I've plotted the amount of gas as traced by HCN, and here I've got the amount of molecular gas as traced by the CO molecule. And on the y-axis, I've got the star formation rate in that gas. All right, and these samples represent pieces of entire galaxies. So a line of slope 1 corresponds to a constant star formation time. All right, that is, if I've got, say, 100 solar masses per square parsec of gas, I form, say, 1 solar mass per square parsec per gigayear of stars, 10 times as much gas, 10 times as much stars. So that's a constant time of star formation, what I'll call the depletion time, the time it would take to convert all of the gas to stars. And what I've done is I've normalized this by the free fall time, that is, by how quickly I would expect gas of that density to collapse if no force but gravity were acting on it. All right, so this line corresponds to a depletion time of 100 free fall times. All right, and that's that factor of 100 I told you about before. All right, that the star formation rate that we observe is about 1/100th of the mass divided by the free fall time. And what you can see is the data fall about along that line. This is for these 2 particular galaxies, but I could show many more examples. Now here's the thing. If you look at this HCN gas, you see it falls along the same line. All right, now this gas is much, much denser, so its free fall time is much, much shorter. And the total mass of this gas is much smaller than the mass of the less diffuse gas. But those 2 factors, it turns out, cancel out and you get a constant freefall time to depletion time ratio. Now, you can do this with other ways of measuring the gas, and here's the result. The ratio of the freefall time to the depletion time is roughly constant. This data point is an upper limit. All right? Now, this is over a very broad range in gas density. This is a factor of more than 1,000 in gas density. And this ratio of freefall time to depletion time is staying about constant. It's about 1% everywhere. All right, now, this is sort of embarrassing. And it's sort of embarrassing, meaning that, all right, so you'd think that I'm looking at interstellar gas that's collapsing to form stars. All right? There had better be some gas whose density is, say, twice the density or half the density of a star. All right, so it's the stuff that's on its way to collapsing. It's all going to be in a star one free fall time later. This gas is going into a star and nothing's going to stop it. So at some point, this diagram had better turn upward. I'd better find gas where every gram of matter I look at is going to be in a star one free fall time later. But over this huge range in density, I haven't found it yet. So in effect, I look at these giant molecular clouds and I say, well, all right, maybe they're not forming stars efficiently. I shouldn't focus on them. Let me go look at the denser gas within them. So I go over to this point. Turns out these things aren't forming stars efficiently either. So I go look at the denser gas within them. Nope, not those either. So in effect, my theory of star formation is it's turtles all the way down thus far. All right, every time I look at some structure and I think this is the stuff that should form stars efficiently, it isn't. So can we understand where this number comes from? So I've renamed this ratio of the depletion time to the freefall time epsilon FF. All right, you can think of it as sort of the efficiency of star formation. All right, so what sets this efficiency? Well, here's a hint from observations. This is a map of a star-forming molecular cloud. This is called the Pipe Nebula. All right, it's called that because you can see there's the stem, there's the bowl, and there's the smoke. The Pipe Nebula. All right, to be an astronomer, you have to be creative with your naming. All right, now, what I want you to notice is that there are these little dense knots that have been circled here. All right, and then there's this sort of diffuse, smoky stuff. Now, it turns out that most of the mass is in that diffuse, smoky stuff, not in the little dense knots. That is, by mass, only about 1% is there, 99% is there. Now, this is a familiar number, or hopefully it is to you. About 1% of the mass is in the cores, I'll call them, and the rest is in the envelopes. Yes, question?
This mass is measured by what?
Velocity or by interaction or by non-interaction?
So the way, right, so in this case, the way this mass is measured is by dust extinction mapping. So let me back up and explain. So what you're seeing here is a map of how much the background light is blocked out by this foreground gaseous material. So what's blocking out the light is the fact that there are dust grains mixed in with the gas. All right, and so there are dust grains mixed in with the gas, and they absorb background light. So what you do is you look at this region, and you find a bunch of stars that are behind it. All right, and for each star, you measure how much of its light has been absorbed out. And the way you can get that is by looking at how much its luminosity is decreased and how much its color is changed, because dust absorbs blue light more than red light. So you look at how reddened the star is, and based on that, you can estimate along each line of sight to a given background star, what's the column of dust grains that I'm looking through. All right, so you make a map like that with many, many stars, and then you've got an estimate of what's the dust column at every point. And so then I just say, well, if I want to know what's the mass in a given structure, well, I take the area of that structure, I multiply by the dust column, and then I multiply again by a factor to correct for the dust to gas ratio. So that's how the masses are measured. Other question?
I'm sorry, I missed
Yes.
the beginning, I was late. Are you saying that more or less there are fewer stars forming now than previous times?
No, the star formation rate in the Milky Way has been about constant for the last...
And it's constant with the death rate, so they balance?
No, it's not constant with the death rate. So the Milky Way is growing in mass.
Oh, okay.
All right, so the Milky Way is, so what's not constant is the mass of the galaxy. The galaxy is accreting from the intergalactic medium. And what balances is the rate of star formation balances the rate of accretion of intergalactic gas. And the death rate is a small correction to that. The number of stars is increasing with time. Yes?
Can you just explain a little bit more what the free fall time is? Is there any ionization of the gas or temperature of the gas
Okay.
included in that? Or?
So empirically, this is all neutral gas and it's very cold. So how do I compute the free fall time? All right. So the way I compute the free fall time is I say, suppose that I've got a gaseous medium that is gravitationally unstable, subject to what's called the Jeans instability. All right. That is, its pressure is insufficient to prevent its collapse. All right. And I ask, well, all right, I've got this medium that's in that condition. Its pressure is insufficient to prevent its collapse. How quickly would it collapse to a singularity if there were nothing to stop it from collapsing? So its pressure is insufficient. If there's nothing else that will stop it from collapsing to a singularity, how long would it take to get to that singularity? That's what the free fall time is.
So you have a collision rate estimate?
It's not from collision rate. It's actually from gravity. You can get the so the way the calculation is done is actually to consider pressureless collapse. All right, and you can show that including pressure only changes it by a small factor if you've got something that's gravitationally unstable. All right, and the reason is if you're even a little bit out of balance between pressure and gravity, as the thing collapses, gravity starts to dominate more and more, and it becomes a runaway. So even if you start just a little bit out of balance, you will very quickly run away to gravity being completely dominant. So you can actually get the free fall time just by considering pressureless collapse. So formally, in fact, I can tell you the exact problem that is used to define the free fall time. Consider a uniform density sphere of gas that is pressureless and which collapses under its own gravity. At what time does the gas reach the central singularity? All right, and it turns out that that time is a function only of the density of gas interior to the point that's collapsing. All right, and that's what defines the free fall time. All right, so now I showed you the observation. Now I'm showing you a simulation. So these giant molecular clouds are extremely turbulent. The gas within them is moving around at something like a Mach number of 30. So on the left here in this simulation, and I should say this is a radiation hydrodynamics simulation done by Stella Offner, and I'm one of the et al. There. She is now a postdoc at Harvard and was a grad student at Berkeley. All right, so here's the gas density, and here is the radiation temperature, which is marking where stars are forming. So what you can see is that the structure of that observed cloud is sort of mirrored in this simulation. There's all this sort of diffuse gas, which isn't doing anything, and then there are these little high-density points that are lighting up with star formation. So this is what we think a molecular cloud might look like. So let me tell you a story about where that epsilon FF comes from. All right, so to explain this, I have to walk you through a little bit of the physics of turbulence and giant molecular clouds. All right, so the first thing I'm going to tell you is that on large scales, these giant molecular clouds, these star-forming structures, have a potential energy that's about equal to their kinetic energy. All right, that is, they're marginally gravitationally bound. All right, and this ratio alpha is just the ratio of kinetic to potential energy, so it's about 1. All right, and that's called the virial parameter. All right, which is to say these giant molecular clouds are sort of marginally gravitationally bound in balance between internal turbulent pressure and their own gravity. Now, the turbulence within those clouds obeys something called a line-width size relation. All right, and this is actually a generic feature of supersonic isothermal turbulence. You can demonstrate it in a computer. You can actually prove it from Berger's equation from first principles. All right, so here is this property. The property is that let me consider some box of gas within this cloud. And let me measure what is its velocity dispersion. That is, at every point I calculate the velocity minus the mean velocity, and I square it, I sum, and I take the square root. So what's the RMS value of velocity minus mean velocity? All right, and I get a certain value. And I do that for all these boxes whose size is L within my cloud. All right, then I consider, say, a bigger box. And I repeat that exercise. I calculate the velocity dispersion in all those bigger boxes. What I will find is that the velocity dispersion I measure depends on the size of the box. The bigger my box, the more velocity dispersion there is within it. And the velocity dispersion varies as the size of the box to the 1/2 power. All right, and the way I've normalized this relation is CS is the gas sound speed, the isothermal sound speed, and lambda s is the size of box I have to pick so that the velocity dispersion is equal to the sound speed. All right, so molecular clouds obey that. All supersonically turbulent structures do. It's a generic feature of supersonic turbulence. So let me pick out some region within my giant molecular cloud at random, and let's make its size L. Well, what are its energies? Well, it's got a kinetic energy and a potential energy. The kinetic energy, well, the mass of this region is going to go something like its volume, like L cubed. All right, so the kinetic energy, well, that's mass times velocity squared. So that's m times sigma squared. So that's like L cubed times L to the first power. So that's L to the fourth power. How about its potential energy? Well, potential energy is like mass squared divided by radius. So mass squared, that's L to the sixth, divided by size, that's L to the fifth. So the kinetic energy varies like L to the fourth, and the potential like L to the fifth. So if I started the entire cloud and kinetic and potential are equal, as I shrink to a smaller region, the kinetic energy goes down, but the potential energy goes down even faster. So the average region within this cloud is gravitationally unbound. It's got much more kinetic energy than potential energy. It can't hold itself together, and that's why it doesn't form stars. Now let me turn this around. Suppose I want to look not for the average region, I want to look for the unusual region, the thing that's going to form stars, the thing that in this movie you saw lighting up. Well, those regions are denser than the average. How dense are they? Well, my hypothesis will be that I only get stars in regions where the potential energy is actually bigger than the kinetic energy. So I have to find some region that's denser than the average. And how much denser than the average does it have to be? Well, this is a problem you can do with some simple algebra, and I will spare you the algebra and just show you the result. The condition on the density is that this lambda j, which is called the gene's length, has to be smaller than that sonic length I introduced earlier. All right, so you can see as I turn up the density here, lambda j, the gene's length goes down, and eventually it becomes smaller than the sonic length. All right, so what does that get me? Well, I now have a critical condition on the density for a region to be dense enough that it's going to form stars. Well, let me tell you something else I know about supersonic turbulence. It turns out that supersonic isothermal turbulence produces a log-normal probability distribution of densities. So let me unpack that statement for you. All right, so I've got my molecular cloud, and it's turbulent, and it's supersonically turbulent. What that means is that if I stick a probe at a given point in that cloud, it's constantly going to have shock fronts running over it from every direction. And it's going to have rarefaction fronts passing through it. And every time that happens, its density is going to change. All right, a shock front runs over it, the density goes up. A rarefaction front passes over it, its density goes down. Suppose I put a probe at that point and I measure what fraction of the time is the density a given value. And I just make a plot of that distribution. That's the probability distribution function of densities. All right, and it turns out that that probability distribution function of densities is shaped like a log-normal distribution. That is, it's a Gaussian in the logarithm of the density. All right, and in fact, if you want to know why, ask me later. I can prove it in terms of the central limit theorem. So this is, in fact, a log-normal density distribution for a particular, so it depends on the Mach number of the turbulence. And I've drawn this critical line for where the density is such that the gene's length is equal to the sonic length. Well, the stuff to the right of this is gravitationally unstable and will make stars. The stuff to the left of it isn't. All right, and I can actually calculate what fraction of the mass is to the right of that line. All right, so I just do an integral and I say that stuff makes stars every free fall time. And it depends on two numbers, depends on the virial ratio of the cloud. All right, that is, how are the kinetic and potential energy balanced on the large scale, and that's always about 1, and it depends on the Mach number of the turbulence. And here's a little movie. All right, as I make the cloud less and less bound, this line moves to the right, less of it forms stars. As I change the Mach number, this line moves right, but also this distribution gets wider. All right, when you actually evaluate that integral, and it turns out you can actually solve it exactly in terms of error functions, but observational astronomers get scared when they see an error function, and so I have a power law approximation to it. Now, notice that coefficient. It's about 1%. What this means is that for any supersonically turbulent object that is roughly virialized, I should get 1%. And all of those things I was plotting earlier are supersonically turbulent virialized objects. So where is the bottom turtle? Where does it stop? Well, it stops at the size scale where things are no longer supersonically turbulent. Those things form stars efficiently, and so that's actually a prediction that can be checked. And let me just say, so that was a nice story. It actually stands up quite well when you check it in a computer. All right, so this is some work done by Padoan and Nordland, and the lines there are the theoretical predictions for hydrodynamics and magnetohydrodynamic turbulence. And the symbols are the results of some simulations where they actually checked what's the star formation rate in the simulation. So it works quite well. All right, I'm almost out of time, so let me end with my last embarrassment. Where in a galaxy do stars form? What part of a galaxy do stars form? Well, here's a map of a bunch of nearby galaxies in H1, atomic gas. All right, now let me fade to a map showing where the star formation in those galaxies is. Now you'll notice those pictures just got a lot smaller. That is, there's all this H1 out here. And as far as star formation is concerned, it is doing absolutely nothing. It's inert. So stars don't form in just any old interstellar gas. They form only in the molecular gas. That is, where the gas is H2, H subscript 2. So this is another version of that plot I just showed you, where at every pixel of one of those maps, the things team, things stands for the H1 Nearby Galaxy Survey. These are the same sorts of people who come up with names like the Pipe Nebula. All right. So at every pixel, they've extracted what's the amount of atomic gas in that pixel, what's the amount of molecular gas in that pixel, and what's the amount of star formation in that pixel. And they've plotted them against each other. And what you see is that star formation versus H1, there's basically no correlation. Star formation versus molecular gas, on the other hand, there's this beautiful correlation with a slope of 1. Incidentally, that line is the sensitivity limit of the observation. That's why things cut off there. So, can we understand where in a galaxy things will turn from H1, atomic gas, into H2, molecular gas? Well, to explain that, I have to first answer the question of why is most of the interstellar medium H1 and not H2? Well, it turns out that stars don't just put out ionizing photons. They also put out dissociating photons. That is, photons that have enough energy to break apart an H2 molecule. All right, so it takes 13.6 eV to ionize a hydrogen atom. But the binding energy of the H2 molecule is only 4.5 eV. So there are a lot more photons that can dissociate molecules than that can ionize atoms, and a lot more stars can put them out. And whereas there are only enough ionizing photons being put out in our galaxy to ionize these little bubbles in a mostly atomic medium, there are enough dissociating photons being put out that the entire galaxy is basically dissociated. All right, so whereas you can think of the ionization as being like holes in a sponge, all right, the dissociation you have to think of as the opposite. The background medium is fully dissociated, and the only place where you get molecules is in very, very dense and unusual regions that are able to shield themselves against this dissociation. All right, so the dissociating photons are what are called Lyman-Warner band photons. That's the name of the particular spectral bands that yield the dissociation. So here's a picture. Here is an atomic molecular complex, and the outer part is H1. And it's H1 because all these Lyman-Warner photons are constantly hitting it and breaking any molecule that forms. But as I move into this complex, more and more of those Lyman-Warner band photons get absorbed until I get to the center and there are none left. And at that point, the gas is free to form H2, molecular hydrogen. All right, so here is like one of my few equations here. So this system is described by two equations, chemical equilibrium and radiative transfer. All right, and let me unpack these equations for you because they're less intimidating than they look like. The equation of chemical equilibrium says that the rate at which H2 molecules form, and that's the number density of atomic hydrogen times the number density of dust grains, and it turns out to be dust grains because the formation process is mostly catalyzed on the surfaces of dust grains, is equal to the rate at which H2 molecules get destroyed by photons. So that's the number of targets times the cross-section per target times the flux of photons that can destroy these atoms times the dissociation probability per absorption integrated over frequency and direction. All right, and then I have the equation of radiative transfer, which says that as I move along a ray going into this cloud, the intensity of photons along that ray decreases because photons are getting absorbed by molecules and because they're getting absorbed by dust grains. All right, so I'm going to solve the following idealized problem. I'm going to consider a spherical cloud whose radius is r, number density is n, specified dust opacity, rate coefficient for H2 formation, and I'm going to immerse it in a uniform isotropic radiation field, and I'll specify the number density of photons. And I'd like to find what fraction of the mass is in this outer H1 part versus in this inner molecular part. All right, and I will spare you the algebra. It turns out the answer depends on these two dimensionless ratios of the parameters. One is the dust optical depth of the cloud, and that's just a way of measuring how big it is. The other is, now for those of you who are astronomers, this will look sort of like an ionization parameter. It's basically the ratio of photons to baryons, photons to matter particles. All right, and if I tell you these two, you can figure out what fraction of the mass is molecular, and just to prove that, all right, so the solid line there is a theoretical model for the atomic gas depth as a function of this parameter, and all these points here are exact numerical calculations. And so we can get that quite well, all right, where we varied the radiation intensity over a factor of, that's 10 to the 6 or so. All right, and since I am running out of time, I am going to skip through the details and just go directly to the punchline, all right, which is that, all right, well, so now I have a way of calculating what fraction of the ISM at a given point is going to be atomic versus molecular. And I already told you, I know once I've got molecular gas, that it turns itself into stars at a certain percentage of the mass per freefall time. So if I put those two together, I can make a theoretical model for the rate at which stars form as a function of the amount of gas. So that sigma there is the surface density of gas. It's the gas per unit area in a galaxy. And I have a prediction for the star formation rate per unit area. All right, so all the colored data points there and the contours are observations. And the solid line there are theoretical models. All right, and the different models that split apart here, they split apart because the amount of molecular gas depends on the amount of metals in the gas, which controls the availability of dust grains to make hydrogen molecules. So few metals, few dust grains, low star formation rate, more metals, higher star formation rate. All right, so I am at the end. So here's my summary. We can measure star formation rates reasonably well from well-established physics. All right, so what goes into this measurement is the physics of the hydrogen atom, which we understand pretty well, the physics of stellar structure, which we understand pretty well, and the weak link here is the initial mass function. That is the distribution of stellar masses at birth, which we can measure empirically but don't really understand. All right, but given all those ingredients, you can, in fact, quite well measure the star formation rate in the galaxy, and we actually know it to within a factor of 2, maybe 3. All right, but we're only at the beginning of understanding the physical processes responsible for controlling that star formation rate. All right, so we have some idea of why it is that stars form so slowly compared to what you might naively expect. And we think it has to do with the turbulence that is ubiquitously present in molecular clouds. All right, but we are only at the beginning of that story. And that's where I will end and take any further questions. Thank you. Yes.
Okay, excuse me, for questions, you ask in the microphone.
Okay. Our star's way out on our galaxy. Did it form that way, or did it move from the hot spots in the middle?
So that is an excellent question. All right, so the honest answer is we don't really know. So most stars do form towards the galactic center, but closer to the center than we are, but a reasonable number form out where we are. So the sun's orbit is not highly elliptical. And so if it did move outward from the galactic center, or from closer to the center, then the mechanism for moving it outward must have been able to do so while keeping it on a non-elliptical orbit. Now, there are plausible mechanisms that can do that, and in fact, the sun appears a little bit more metal-rich than you might expect from its location in the galactic disk, which might suggest that it did come from a little bit further in, but really, it's very, very difficult to tell. So we don't honestly know the answer to that question.
But there are high-mass stars forming out far in the galaxy, so we know that.
Oh yes, definitely. There are.
We know that there's star, that there is star formation.
Oh, there's absolutely star formation where we are in the galaxy. So it's not,
Even way beyond.
and beyond it. It's not at all implausible the sun could have formed at its current galactocentric radius. The star-forming disk extends beyond our radius.
So the point about H2 is just a tracer of density, right? So you said in the outer parts of the galaxies where it's just H1, not molecular hydrogen, there's just no molecular hydrogen because the density is not high enough, there are not dust grains. What's the...
Yeah, so it's a combination of the gas needs to be dense enough, and not just sort of volume density, but column density. This is a process of shielding, all right? So there are all these photons running around interstellar space that break hydrogen molecules in two. And the only place where you get appreciable populations of hydrogen molecules is where you've got a big column of gas that shields against those photons. So what you need is not just a high volume density of gas, you need a lot of it collected into a shield in front of you to protect you from being dissociated. So that's what's missing in the outer galaxies. There aren't a lot of high column density regions that can protect themselves and allow molecules to form.
In the picture of the pipe galaxy,
Of the Pipe Nebula?
yeah, the pipe
Okay.
nebula, you were saying the mass measurement was dependent on how much photon absorption was happening between the source and the gas and the dust particles in between.
Yes,
And you're getting your mass information from there.
that is correct.
Do you consider, does the dark energy, dark matter, near the center, you'll get closer to the center of galaxy, or in the galaxy you also have dark matter, and closer to the center you have the effects of the central black hole.
Okay, so first of all, I should say this isn't a galaxy. This is in our galaxy. This isn't an external galaxy. So are there effects from dark matter? We don't think so, which is why it's dark. If it interacted with light, that'd be great. Then we could detect it. So, sort of by definition, its interaction with light is, either none or very, very little. So you don't have to worry about that. Do you have to worry about the black hole? You can't see directly through the black hole, but the black hole subtends a tiny, tiny, tiny fraction of the sky. So this is nowhere near the direction of the black hole. And a bigger problem is that for observing in the galactic disk is that there's a lot of dust in the galactic disk. And so, you can't even see as far as the black hole in visible light because it all gets blocked out by the dust. So when you see those beautiful observations of stars going around the central black hole, those are all done in the infrared because that's the only place you can actually see through the dust far enough to see those stars. You look at the galactic center in optical light, you see just nothing. You see, the dust clouds in between us and it.
Is there any hints that dark matter might play a role, or is that we expect it to be too weakly interacting to
Play a role in star
star
formation?
formation?
Well, so at the largest scale, it creates the potential wells in which galaxies form. All right, so yes, it has that role to play. But once you're within a galaxy, it is not expected to be significant because the dark matter distribution is quite smooth because it's not interacting. All right, so there's this big gravitational potential well created by the dark matter. All right, but once you're in it, once you're in the galaxy, there are no strong forces because the distribution of matter is very smooth. So the gradient of the potential is small inside the galaxy. So on this size scale, so I mean this is an object that's a few parsecs in length, on that size scale, the dark matter distribution is completely uniform. And so, or is thought to be quite uniform, and so you don't expect there to be significant forces due to the gravity of dark matter that are different from, say, one end of this to the other.
All right, one last question.
If you need really specific, conditions to form in star-forming regions, like the molecular hydrogen with the shielding around it, as those become exploited, wouldn't you expect the rate of star formation to decrease?
Well, so individual star-forming regions do indeed turn off. So a giant molecular cloud probably lives, our best estimates are, sort of 30 million-ish years. All right, and then it's done. All right, so in fact, it doesn't get depleted in the sense that it turns all of its mass to stars. The stars actually blow it up. So it forms a few stars, and those stars blow the rest of it up. So if there were no way to make new molecular clouds, then indeed that's what would happen. However, this is balanced by new molecular clouds being created out of gravitational instability in the galactic disk. And so we appear to be in roughly a steady state between molecular clouds being born and molecular clouds being blown up by the stars they form. So what really sort of limits you, what turns off star formation is, so the star formation rate, has decreased over cosmological time. And what's driving that decrease is that galaxies are accreting gas less quickly. If you ask on the largest scale, what limits how fast a galaxy can make stars over cosmological time scale? What limits it is the supply of gas into that galaxy from the intergalactic medium. And as the universe has expanded more and more, and the intergalactic medium has gotten less dense and galaxies have gotten further apart, the rate of accretion onto galaxies has indeed gone down. And so that has caused star formation to taper off. So on the largest scale, that's what limits the star formation rate, is just the mass supply.
All right, well, I encourage you to bring any additional questions up to the speaker in person, and let's thank our speaker again.